Hello students, I am Dr. Sujit Agrawal. I am Associate Professor in the Department of Applied Sciences and Humanities, Kamala Nehru Institute of Technology, Sultanpur. And we are studying module 2 electromagnetic field theory. This is module 2 of BTech course KAS 101T and KAS 201T. This one is the sixth lecture of the lecture series on electromagnetic field theory. So, let us see what we have learned in previous lectures. In previous lectures, we learned integral and differential forms of laws of electricity and magnetism and some mathematical concepts. Then we learned continuity equation for current and modification of Ampere's law for time varying electric and magnetic fields, and then displacement current and its physical significance. After that, Maxwell's electromagnetic equations in integral and differential forms and their physical significance, and then electromagnetic waves in free space, propagation of plane electromagnetic waves in free space, phase relationship between electric and magnetic field vectors of plane electromagnetic waves, and transverse nature of electromagnetic waves. All this we have learned in previous lectures, and what we are going to learn in this lecture, let us see. In this lecture we will discuss electromagnetic waves in non-conducting media and electromagnetic waves in conducting media. Okay. So, let us start electromagnetic waves in non-conducting media. So, Maxwell's equations of electromagnetism are these equations. Number 1, del dot E equal to rho by epsilon 0, where E is electric field and rho is volume density of charge, epsilon 0 is permittivity of free space, and the second equation is del cross E equal to minus delta B by delta T. This is Faraday's law of electromagnetic induction. Here B is magnetic field, T is time, and third equation is modified Ampere's law, del cross B equal to mu j plus mu epsilon delta E by delta T. J is current density and mu is permeability of the medium. Okay. And the last one is del dot B equal to 0, divergence of magnetic field is 0. So, these are Maxwell's equations of electromagnetism. Now, for non-conducting media, we can substitute rho equal to 0 and j equal to 0 and B equal to mu h. Rho is volume density of charge. In non-conducting media, there are no free charges. So, rho equal to 0 and current density J is also equal to 0, and we can substitute B equal to mu h, where h is magnetic field. H is magnetic field in ampere per meter. Magnetic field B is in Tesla, while magnetic field H is in ampere per meter. So, Maxwell's equations for non-conducting media will become number 1, divergence E equal to 0, del dot E equal to 0, and the second one will become del cross E equal to minus mu delta H by delta T, and del cross H equal to epsilon delta E by delta T, and del dot H equal to 0. These 4 equations will be equations for non-conducting media. Now, let us take curl of Faraday's law. Faraday's law is del cross E equal to minus mu delta H by delta T, and let us take curl of this equation. So, in on the left hand side we have del cross curl of E equal to minus mu delta T delta by delta T of del cross H. Now, the left hand side we will expand the left hand side using vector identity. So, let us use vector identity curl E equal to gradient divergence E minus del square E, where the operator del square is given by this equation. Operator del square is given by this equation. So, we can expand the left hand side of the equation curl E equal to minus mu delta by delta T del cross H using this vector identity, and then we get gradient of divergence E minus del square E equal to minus mu delta by delta T of del cross H. Okay. So, we have got at the end we have got this equation gradient divergence E minus del square E equal to minus mu delta by delta T of del cross H. So, these are the Maxwell's equations for non-conducting media, and now here we have divergence E equal to 0 and del cross H equal to epsilon delta E by delta T. So, we will substitute we have got this equation in the last slide gradient divergence E minus del square E equal to minus mu delta by delta T of del cross H. So, in this equation we when we substitute divergence E equal to 0 and del cross H equal to epsilon delta E by delta T, what we get? We get minus del square E equal to minus mu delta E by minus mu delta by delta T of epsilon delta E by delta T, and when this equation is simplified, we get del square E minus mu epsilon delta 2 E by delta T square equal to 0. Similar equation we can obtain for magnetic field also. So, let us see how. If we take curl of del cross H equal to epsilon delta E by delta T, if we take curl of this equation, then we will have curl H equal to epsilon delta by delta T of del cross E. Now, we can expand the left hand side curl H by using vector identity curl H equal to del dot H means gradient divergence H minus del square H. So, when we expand left hand side with this vector identity, then what we get? We get this equation reduces to this equation. Left hand side is expanded using this vector identity. So, we have gradient divergence H minus del square H equal to epsilon delta by delta T of del cross E. Now, we can substitute for del cross E. From this equation, and then we have del cross E we can substitute, and also del dot H we can substitute del dot H. from this equation. So, del dot H equal to 0 and del cross E is minus mu times delta H by delta T. So, this equation becomes minus del square H, left hand side what we get in left hand side, this term goes to 0 and we have minus del square H equal to epsilon delta by delta T of, and value of del cross E is substituted from here. So, minus epsilon delta by delta T mu delta H by delta T, and this equation reduces to this equation del square H equal to del cross H del square H minus mu epsilon delta 2 H by delta T square equal to 0. So, we get two equations for electric field and magnetic field, this equation and this equation. These two equations for electric and magnetic fields when electric and magnetic fields are time varying. Okay. So, what these equations represent, let us see now. For non-conducting media, we have obtained these two equations in the last slide, del square E minus mu epsilon delta 2 E by delta T square equal to 0 and del square H minus mu epsilon delta 2 H by delta T square equal to 0. So, these two equations, these equations show that both E and H, electric field and magnetic field H, both satisfy this wave equation, del square psi minus 1 by V square delta 2 psi by delta T square equal to 0. This is a equation of a wave. How? We have learned earlier that we can write equation of a plane progressive wave as psi equal to psi 0 sin 2 pi by lambda V t minus x. If I differentiate this equation with respect to x twice and with respect to time twice, then this equation can be written as this equation. This equation satisfies this equation. The usual equation of plane progressive wave satisfies this equation, and this is written in one dimension. Okay. If I write this in 3 dimension, then this delta 2 by delta x square will be replaced by del square, operator del square. So, the equation del square psi minus 1 by V square delta 2 psi by delta T square equal to 0, this equation is of type, this equation is equation of wave, and these two equations, these equations are of this type of equation. If I compare this equation by these two equations, then what is at the place of V velocity? Here V is velocity of the wave. This indicates that the fields E and H varying in space and time propagate as waves. That is, electromagnetic waves exist in nature. If E and H are time varying, then they propagate as wave with velocity v. And what is the velocity v? This can be obtained by comparing these two equations. Let us compare this equation with this equation or this equation. Then I have mu epsilon at the place of 1 by v square. So, this gives velocity of wave as 1 upon root mu epsilon. Now, if mu 0 is permeability of free space and mu is permeability of the medium, then relative permeability is defined as mu r equal to mu by mu 0, and relative permittivity is defined as epsilon r equal to epsilon by epsilon 0. So, I can write mu equal to mu r mu 0, and similarly epsilon I can write as epsilon r epsilon 0. So, in this equation I can write mu as mu r mu 0 and epsilon as epsilon r epsilon 0. Okay. So, here I have 1 upon square root mu r epsilon r into 1 upon square root mu 0 epsilon 0. Now, 1 by root mu 0 epsilon 0 is c, which is velocity of light in free space. This was derived when we learned propagation of electromagnetic waves in free space. So, this is c, velocity of light in free space. So, I have this velocity of electromagnetic wave in a medium is c by square root mu r epsilon r. Okay. So, now we will study electromagnetic waves in conducting media. Maxwell's equations of electromagnetism are rho by divergence E equal to rho by epsilon 0, curl E equal to minus delta B by delta T, and curl B equal to mu j plus mu epsilon delta E by delta T, and divergence B equal to 0. These 4 equations are Maxwell's equations of electromagnetism. In case of non-conducting media, we had substituted rho equal to 0, current charge density rho equal to 0, current density J equal to 0, and B equal to mu h. In case of conducting media, charge density rho is 0, because conducting media has free charges and which can move. So, current density is not 0. So, in case of conducting media, we can put rho equal to 0 and J, current density J equal to sigma E, and B equal to mu h. Magnetic field B, this B is actually magnetic induction field, which is written in Tesla, and H is called magnetic field, which is in ampere per meter. Okay. So, this way you can differentiate simply, just differentiate between B and H. Sigma is the conductivity of homogeneous and isotropic medium. So, with these substitutions, equations of Maxwell's equations for conducting media become number 1 del dot E equal to 0 and del cross E equal to minus mu delta H by delta T, and del cross H equal to sigma E. J is we have substituted sigma E for J. So, del cross H equal to sigma E plus epsilon delta E by delta T, and divergence of magnetic field equal to 0. So, these 4 equations we have for conducting media. Now, as we have done earlier in case of free space and non-conducting media, similarly here also we will take curl of Faraday's law. Faraday's law means curl E curl E equal to minus mu delta H by delta T. This equation, let us take curl of this equation. So, we have on the left hand side curl E equal to minus mu delta by delta T of del cross H, and further we will expand left hand side using this vector identity. Curl E equal to gradient divergence E minus del square E, where del square operator del square is defined by this. Del square is equivalent to delta 2 by delta x square plus delta 2 by delta y square plus delta 2 by delta z square. So, when we expand left hand side using this vector identity, we obtain gradient divergence E minus del square E equal to, in this equation left hand side is replaced by gradient divergence E minus del square E equal to minus mu delta by delta T of del cross H. So, in the last slide we obtained this equation, and what we do now, Maxwell's equations for conducting media we have written in the last slide. Number 1, del dot E equal to 0 and del cross E equal to minus mu delta H by delta T, del cross H equal to sigma E plus epsilon delta E by delta T. H is magnetic field in ampere per meter, not in Tesla. If you write magnetic field in Tesla, then it is B field. Okay. So, and del dot H equal to 0. These 4 equations are Maxwell's equations for conducting media. Now, del dot E equal to 0. So, here this term will go to 0, and del cross H we can substitute from this equation. So, let us see, this del dot E equal to 0 and del cross H is sigma E plus epsilon delta E by delta T. So, this equation becomes minus del square E equal to minus mu delta by delta T of sigma E plus epsilon delta E by delta T, and when it is simplified it gives del square E minus mu epsilon delta E by delta T minus mu epsilon delta 2 by delta T square. In case of non-conducting media and free space, this term did not exist, in which we have single derivative of electric field with respect to time, but in this in case of conducting media we have this term also. This equation is still a equation of a wave. We will see later how. So, for electric field we have got this equation. Similarly, a similar equation we can get for magnetic field also. So, if we take curl of modified Ampere's law, if we take curl of this equation, then we have del cross H equal to sigma and del cross E plus epsilon delta by delta T of del cross E. We have taken curl of the whole equation. So, again we will expand left hand side, this term by using vector identity. Which vector identity? This one, curl H equal to gradient divergence H minus del square H. So, when we expand this equation, we have left hand side becomes this, and in the right hand side we can substitute for del cross E from this equation. Okay. So, and del dot H is also 0, del dot H, this is 0. So, we get minus del square H, this term goes to 0. So, minus del square H equal to sigma times mu sigma minus mu sigma delta H by delta T minus mu epsilon delta 2 H by delta T square, this equation. So, in case of conducting media, we have electric field satisfies this equation and magnetic field satisfies this equation when electric and magnetic fields are time varying. Okay. So, let us do one problem. Determine the conduction current and displacement current densities in a material having conductivity of 10 to the power minus 4 Siemens per meter and relative permittivity epsilon r equal to 2.25. The electric field in the material is 5 into 10 to the power minus 6 sin 9 into 10 to the power 9 T volt per meter. In this equation, in this problem, we have conductivity sigma equal to 10 to the power minus 4 Siemens per meter, relative permittivity epsilon r equal to 2.25. Therefore, permittivity is epsilon r epsilon 0. So, it is 2.25 multiplied by 8.86 into 10 to the power minus 12 Coulomb square plus Coulomb square by Newton per meter square, and electric field E is 5 into 10 to the power minus 6 sin 9 into 10 to the power 9 T volt per meter, and J is given, sigma is given, E is given. So, I get J equal to sigma E, and displacement current is epsilon delta E by delta T. So, I can differentiate E with respect to time, and I can get J D displacement current also. So, that is all for this lecture. In the next lecture, we will study electromagnetic waves in conducting media, plane wave solution, and damping of electromagnetic waves, attenuation constant, skin depth, etc. Thank you.